Hello and welcome to this section of the course. My name's Gerd Berner and today I'll be presenting system integration as part of maritime IT systems and security. What are we speaking about when we refer to integration? We're talking about interconnecting systems so that data from one can enhance the operation of another. Historical technology systems found on vessels were single function devices. If you look at a radar system from the 60s or 70s, it received no data from any other system. It was a discrete piece of technology that was used for a single purpose, and in that era the officer of the watch was expected to use that system for a particular function, move to another station, use that system for its function, and synthesize that data to create a mental model that enabled that individual to do their job. As technology has advanced, and as you can see from the picture at the top right of the slide, technologies evolve whereby we have the integrated bridge, and there's an expectation that a watch officer can stay in a single place and have a picture of a synthesized picture that provides them with a lot of the information that they need at a single glance in one place. Now we still, underlying this integrated bridge, have these distinct systems. We have radar, we have GPS system, speed log, gyro, compass. They are still largely distinct systems, and that is an important consideration for things like redundancy. We might have two gyro compasses in a redundant configuration, the data for which is provided via a technical integration to the ECDIS, to the ARPA, displaying its data on that common screen for consumption. Underlying, we have still those distinct systems. Similarly, in the engine room, we can now have a composite view of system status on a single screen, whereby in the past it was necessary for watchkeepers or watchkeeping ratings to go and collect that information machine side, or reading gauges. Still an effective way of collecting the data, but not in real time. That single view was not available. The advantages are obvious. We can run the system with less human interaction, and we have that ability to cast a glance, scan that common data that's being collected via these technical integrations, and at a glance identify problems and trends. Now we'll talk more about technical integrations in later slides. We'll be considering analog collection of data. We'll also consider digital, and as I said, we'll touch on these in more detail in later slides. So what are the implications of integrated systems? Well, we have additional complexity that needs to be managed, and this is particularly prevalent in the testing of new technology or technology that's been retrofitted to a vessel. We have a different skill set required, both from an engineering perspective and also from an ongoing operational maintenance perspective. This type of automation also introduces dependencies, and it's not difficult to imagine the impact on the integrated bridge when some of these data sources cease to operate correctly. It can throw the usability of the whole solution into chaos. We will talk a bit more about some specific types of integrations, and I've listed 4 there that we will talk through. Ethernet, a common networking standard that many of us may be familiar with. Also CAN bus, serial RS485, NMEA, which is a specific maritime equipment integration standard, and also analog 4 to 20 milliamp, which is found typically in the engine room to measure parameters such as temperatures and pressures. Now, also another emerging type of standard that we are seeing a lot is whereby we need an integration of sea-based systems back to the head office to allow for monitoring and reporting on vessel conduct and efficiency. This is an increasing requirement for many shipping companies, and the majority of vessels are increasingly in touch, either via office protocols like email or directly where we have shore-based monitoring of seagoing systems. This is common in the case of machinery vendors, where you have expensive equipment such as cranes and winches and engines where there's a monitoring element to the support contract that's in place with that particular vendor. The first standard I want to speak about is the NMEA, or National Marine Electronics Association standard. This standard is used to connect devices on integrated bridges and is based on a serial connection. And when I say serial, I mean an interconnection that can only send 1 bit of information, 1 single digit at a time. It's based on RS232, RS488 for those who'd like to look further into that standard. And it's a standard that's been around for many decades. It's relatively slow, only being able to transmit 4,800 bits per second, or around 480 characters per second. Now, for those who have high-speed broadband connectivity, familiar with the Wi-Fi standard, any other standard, will all know that that's ludicrously slow, but in line with our engineering principles, it's fit for purpose and can handle the rate of data exchange between the various devices on the ship's bridge. The standard, as I said, transmits only 1 bit at a time, and if you refer to the phase diagram on the bottom right of the screen, you'll see essentially a waveform, and that shows how the ones and zeros that make up the binary digit that's sent along the wire are comprised. Those binary digits are then transmitted back into readable text using what's known as the ASCII codes, and there's a link there on the page to an ASCII table. For those with a lot of time on their hands, feel free to go through an exercise of taking a binary number and converting it back to a particular alphabetic character. Hours of fun for everyone. Now, as those characters are assembled from the binary digits transmitted down the wire, they become an NMEA sentence. You can see a reference sentence in the screen there. That is just one of many different types of supported sentences within that language. And this particular one is a GPS providing a position to a consumer device. Now, you can probably imagine that this could be, that information could be consumed by an ECDIS, it could be consumed by a voyage recorder, any number of devices that are interested to receive an up-to-date position from a GPS device on the bridge. An upper radar might be another example. Now, when integrating these devices, we need to be clear on who's to consume those events and what the capability is of the consuming device to accurately consume those particular events. There's a testing aspect to this, and it's something to be aware of if you happen to be part of a project to replace certain equipment on a ship's bridge, that the various versions of the protocols are compatible and that the devices are going to act correctly in response to those messages. Now, there is an anecdote that I would like to share. This does date back some years, but it's extremely relevant to this type of integration. The Royal Majesty was a cruise ship, and this incident occurred back in 1995. There was a GPS device on the bridge, and that was feeding the autopilot with a GPS position using NMEA, and probably that exact NMEA sentence that we're showing there on the screen. Now, what occurred was the GPS had a partial failure and could not receive a signal from its aerial on top of the bridge. So the GPS device dropped back into dead reckoning mode. And I'm sure most of us are familiar with the concept of dead reckoning. Over time, the reported position became less and less accurate as the vessel was affected by wind and waves. So with the GPS in dead reckoning mode, it was reporting also using the standard that it was operating in dead reckoning mode, and that consuming devices should therefore take into account the increasing uncertainty around that position. Problem being, the autopilot was not capable of decoding the signal that indicated the GPS was operating in dead reckoning mode. So despite that being reported, it was not being consumed and acted upon correctly. So the only indication that the GPS was operating in degraded mode was displayed on the GPS itself and not in a prominent position. And this led to the vessel running aground. So I did think I would share that anecdote, very topical and specific around integration of technology on ships' bridges. So coming back to my earlier comment around testing, it may seem that it's a trivial matter to interconnect these devices and validate that they appear to be working, but it is important to press the engineers around the testing of those edge cases. Does the consuming device support the full list of protocols within that standard? The next integration type I want to talk about is CAN bus. Now, CAN bus is a game changer when you consider the legacy pattern at the bottom left of the slide, where there's a mesh of varying different cables taking control and signal back to the main control unit from the various points within the network. CAN bus, slightly to the right, operates on a common bus that is chained to the various points in the network, the sensors, the controllers, and at the top right of the screen you can see the concept. We basically have every device on a common bus. We have a sender node and we have receiver nodes. Each node is identified by a unique ID. So a sender that wishes to send what's known as a frame, in a lot of ways like a packet within TCP/IP that some of us may be familiar with, that frame is put onto the bus and given an identifier to the receiver. The receiver then picks that off the wire and operates on the contents of that packet. Now, every other node on the network ignores that packet. Now, it may be on people's minds that why is such a simple paradigm, why has it taken us this long to get to such a simple solution? Well, while it looks simple on the slide, there's a lot of complexity underneath, because we have many potentially devices on the network all wanting to communicate simultaneously. There may be some devices that are more important than others. So we have to, the protocol and the devices have to be engineered to manage these constraints. The priority and the collision, as it's referred to, of multiple devices transmitting at the same time. And we'll talk more about that on a following slide. The benefits are obvious. There's a huge cost saving and a huge reduction in complexity to be achieved by leveraging this pattern. The amount of wiring and cabling is extremely expensive when you consider the level of shielding and cable that's required on board ships due to the electrical noise. The cost of copper cabling, is vast, and by removing all of these variety of different signal cables that would traditionally run back to the central control and running of a single, or more likely a redundant set of CAN bus networks around the engine room, linking in devices as the bus traverses the networks, vast savings to be enjoyed. Signals are digitized in the field so that the CAN bus is only dealing in those digital signals. There's no analog signals, as I've said, having to be transitioned back to the central control point. Redundancy of the bus is critical because obviously we can't have a situation where if that single cable is severed or damaged or fails, the whole network fails. That's not an option, and it's normal for CAN bus transmitters and to support a dual redundant network, so that in the event that one side of the network fails, the other side can continue without interruption. One important point I want to mention at this point is, in our careers as engineers and as mates and as ship managers perhaps in the future, open standards are a wonderful thing. CAN bus is an open standard, and what that means is this standard has been endorsed by the engineering community, and multiple vendors can participate and provide infrastructure and equipment that recognises and can work using the CAN bus standard. Similarly, the serial standard, NMEA. What we need to guard against as consumers and engineers is proprietary standards, whereby a particular vendor might build equipment that will only talk to equipment that belongs within that same vendor ecosystem. This can result in something that we call vendor lock-in because of a lack of compatibility with other equipment from other vendors. Now, many vendors in history have adopted a strategy of proprietary standards, and I won't name names, but thankfully in this day and age, particularly in maritime, there is a broad adoption of these open standards. But it is something to be aware of and to consider in your roles as a future. Okay, this slide follows the previous one and is an extension of the CAN bus discussion. Now, what I wanted to show is this is the makeup of a CAN bus frame. Now, this won't be covered in the exam in any depth, but what I want to point out is the breakdown. If you consider that the through the middle of that picture is a whole long string of binary numbers, ones and zeros, and this shows the full length of that frame that is transmitted across the CAN bus network. First thing to notice is the arbitration field, the first 11 bits, and that covers things like the priority of the message, and also deals with contention. So when a frame is part of a collision, it's managed by the arbitration field. That's how that collision is resolved. You'll notice secondly the data frame, and the data frame only covers 8 bits, and it's really interesting to think how small in a frame whose purpose is to send a piece of data, how few bits within the CAN bus frame actually relate to the data. It's very small. The next point to look at is the CRC field. Now CRC stands for cyclic redundancy check, and this is essentially error checking. So when a receiver node plucks this CAN bus frame off the wire and recognizes that this is for me, it uses that field to recompute the frame and identify whether there's an error within the frame or not. So once again, a large part of the frame related to just computing the error field to understand that the frame is valid or invalid. So yeah, that's the CAN bus frame. What I want to talk about next is analog process control. So what this relates to is controlling a real-world parameter within an active system. So in the case of a cooling system, this will be maintaining a temperature within a liquid, a cooling liquid, or supplying a fuel within a set of parameters to make the system operate within specification. It may be maintaining a tank level and responding to disturbances within that system. So if we look at the diagram, we have obviously a human-machine interface, and at some point the operator needs to provide a set point or be able to monitor the way the system is operating. The HMI then refers to a controller, and the controller is the point in the system where sensed inputs from the process are compared to a set point, and then an actuation will occur to keep the controlled process within specification. So if you consider those 4 blocks at the bottom of that diagram as a continuous feedback loop, this is how it works. The controller checks its set point, it does a comparison, identifies a deviation. If there's a deviation, it drives the actuator to open or close a valve, perhaps, to keep that controlled process within its specification. Now, the point of this analog process control slide is that often the actuators, the connectivity between controller and actuator might be an analog 4 to 20 milliamp signal, and oftentimes that is what you find. The device shown on the right of the screen is exactly that. It's an electrical actuator that can be driven by a controller using a 4 to 20 milliamp signal. So if you imagine a tap at 4 milliamps, the tap will be closed. At 20 milliamps, the tap will be fully open, and that controller will have full ability to affect that change within that range of current. You may well ask, why does the 4 to 20 milliamp standard start at 4 milliamp? Why doesn't it start at 0? Why is the closed signal not 0 milliamps? Well, there's a very good reason for that. And the reason is, if there's a failure in the system and 0 milliamps is reported on the receiving device, that's an indication of an error. So we raise the closed signal up to 4 milliamps to give that error detection capability. So let's consider for a minute what we've learned about electrical integrations and what are the key constraints. So distance. When we integrate electrical equipment, the distance over which they need to be integrated is key, because the longer that distance, the more electrical noise is induced into those cables and the less signal quality can be achieved. Many standards like serial standard RS-232 will only function over relatively short distances. Conversely, speed and distance kind of work together. So the faster you want to transmit data, the less distance you can do it over is a general rule of thumb. When we're integrating equipment, generally the first question that you will ask is what types of protocols do these devices support to allow for them to be integrated? And we'll be looking for those open standard type of integrations like our NMEAs and our CAN bus style of integrations. If a vendor is saying we only support our own native integrations and they're proprietary, that should be a warning sign. Also to consider, if we've got equipment from multiple vendors, it's around what version of the protocols are supported. If there's incompatibility around the versions, that can lead to functionality problems down the track. And of course, the question of cost is always going to be key. How can we do this the cheapest possible way? You know, there may be faster ways of transmitting that data. There may be more expensive. Perhaps we could use fibre optics. Might be a lower opportunity for noise. It may be a faster medium to transmit the data, but do we need it? It comes down to the cost. And we should always have our engineering hat on. That's not to stop us asking these questions when a proposal is put forth to us by an external contractor. Is this the most economic way to integrate this equipment? So in summary, there are many integrations within a vessel. We have them on the bridge and the engine room, and their integrations cross-domain. We also have integrations ashore, whereby vendors and the company are drawing data off particular systems to perform a remote monitoring and support service. Wherever possible, we should embrace open standards to maximize our ability to integrate systems over proprietary standards which allow for vendor lock-in. Integration should always be based on sound engineering principles. They need to be fit for purpose. They need to be tested and make sure that we have full compatibility of standards. And they need to be cost effective. While it may seem prohibitive to be running RS-232 serial NMEA networks within a bridge environment, as long as that's fit for purpose and is a robust solution, then that is the best engineering solution that there is. Always be aware that as officers and potential ship managers in the future, that there's the possibility of shore-based engineers retrofitting or refitting vessels, and issues arising as part of those integrations. And testing is a key part. Testing of integrations to make sure that they provide that full enrichment and they are compatible at both ends. Thinking back to the example of the Royal Majesty, where we had a consuming device that wasn't fully compatible with the standard. That concludes this section of the course. Thanks for your attention. And to refer to any of the references in this section, please refer to the following slide.